Hello. All right, welcome. Today we are going to be talking about some of the scientists that were able to kind of revolutionize what we understood about the atom. Why is this important? Because when we dive into the history of how other scientists made these discoveries, it shows us how experimentation works. And you're going to be able to see a little bit about how the scientific method was employed with some of these scientists' experiments. And you're going to be able to just kind of see how cool it was that they were able to dive into these black boxes of the atom, these unknown things that we couldn't see, and discover some things we'd never known before. So we're in section 3.2, and our objectives today are to talk about Thomson, and he did a cathode ray tube experiment and what he discovered about the model of the atom. And then Rutherford, a guy by the name of Ernest Rutherford, and what he discovered when he did his gold foil experiment and how that worked out. Okay, so when we're done here today, you should be able to describe Thomson's plum pudding model of the atom and how it came about with that, and then explain how Rutherford's nuclear model of the atom was determined and why it's different than Thomson's. Okay, so first of all, let's look at J.J. Thomson's cathode ray tube experiment. This is back in 1897. So you guys have seen cathode ray tubes before. Cathode ray tubes you'll see on TVs, basically old school TVs. The ones that are kind of like the big boxes that are kind of thick. Well, those are cathode rays. The old school computer monitors, those are cathode rays. Cathode rays basically are just little rays of electrons. Of course, they had these tubes before they knew what an electron was, and so Thomson was doing an experiment on one of these. You can see it here. You can see that we basically just have two electrical terminals, and you can see that in this case there's a green ray, and it's actually dipping downward. Okay, so glass tube, two metal plates or electrodes attached to a voltage source. The beam between the two electrodes was deflected by a negatively charged object and or a magnet. Okay, so this beam was being deflected by something negative and or a magnet. It could also be attracted to a positive charge object. So what he was doing by doing this is he was noticing that this little beam is somehow going to be negative because negative makes it go away. Okay, and positive attracts it. So this beam is made out of something negative. Okay, and he figured out those were charged particles, right? Because they were deflected by negative. He also figured out that they had some mass. Now, one of the ways he figured out they had mass, apparently, in one of the experiments, he had like a little flywheel in there. And when he shot this little light ray at this little flywheel, it actually churned. Okay, I haven't seen that experiment in textbooks, but I've read about it and thought that was kind of wild. So anyway, he proposed that there were these particles called electrons that were inside this atom. So what does his model look like? Well, back in those days, they had something called plum pudding, which to us would be raisin pudding because they called raisins plums back then. And so he basically believed that there were these raisins, okay, or electrons, and these were all negatively charged, and these were embedded inside a positively charged goo. So think of pudding, and you guys may not know what plum pudding is or raisin pudding is. Think about raisin bread pudding. It's like a kind of a gooey substance, and then it's got these raisins all scattered out around it. That's kind of the idea. He believed that there were negatively charged particles that were embedded in a positively charged goo. All right, that's called the plum pudding model, and that was his sea of electrons, right? Sea of positively charged material. Sea of positively charged material, and then the negative electrons were kind of embedded inside that. Then there was Rutherford. Now, Rutherford had another experiment, which was really kind of cool. They'd already had, again, something they didn't really understand yet, but they had something called an alpha particle source, which were basically just the helium nuclei that would shoot out of a particular element source, and those little alpha particles are shooting out of this little box. Okay, so imagine this little box here, and that little box is shooting out these helium nuclei. And what he did is he set up a piece of gold foil. Now, gold foil is very thin, but it's still solid. Okay, think of aluminum foil. It's even thinner than that, but it's still a solid particle. Now, what he was doing, he was testing to see if Thomson's model was correct. You'll notice that Rutherford was doing this quite a bit after Thomson had done. So, this theory of Thomson's had been around for quite a while. And so he said, well, you know what? If I shoot these these alpha particles, which are helium nuclei, and they're way bigger, way more massive than electrons, then this particle should be able to shoot right through, okay? Shoot right through the gold foil. If all of matter is just this positive C and it's just goo, I should be able to shoot big particles through just this little goo stuff, right? And so, in fact, he did find that most of the particles, most of those big alpha particles shot through the gold foil. But he found that some of them were deflected and some of them actually bounced back. So this one went through and deflected off, and this one bounced back and hit. Now, he had X-ray paper basically on the inside of this ring, and so he was able to see where particles hit, because wherever a particle hit, it would cause that X-ray paper to glow when they developed it. Okay, so what did this tell him? What was he thinking once he saw this? Well, this is the model he came up with. He said, you know what? I bet what's happening is that these particles that make up gold are mostly empty space. Okay, that's one big thing to remember, because most of the particles shot through. Think of all these ones here that shot through. And so because so many of these alpha particles shot through the gold foil, then matter, this gold, is mostly empty space. Now, that's a crazy idea, right? I mean, think about it. Even today, to you and me, that's still kind of crazy. You are mostly empty space. I'm mostly empty space. Matter is mostly empty space. How crazy is that, right? That's crazy. But that's what he was finding out. Again, a little experiment. And even if it sounds like a crazy idea sometimes in science, you go with the evidence, right? And so you say, hey, I can't really explain it. It seems kind of weird, but that's the evidence, and that's what he took. And so then some of them deflected. Now, you notice this one kind of bounced away, slightly deflected particle. Now, what's happening there is it's a positively charged nucleus, okay? And this is part of what Rutherford came up with. This nucleus is positively charged. It's large and positively charged. And so if another positively charged helium nuclei, this alpha particle, comes near it, the like charges repel each other, right? And so these guys are going to repel away because positive and positive repel each other. Then some of them actually bounce back. Now, this was absolutely flabbergasting to Rutherford. He basically said, you know what, it was as if you took a 15-inch shell. Imagine these big guns on battleships, right? And so you've got a 15-inch shell, like this huge, huge, huge kind of missile-like bullet, right? And this thing hits a piece of tissue paper and bounce back, right? Kaboom! You shoot this thing out and all of a sudden it hits tissue paper and bounce back. It's like, no, there's no way this should happen. And that's kind of what he was saying. If this is all empty space, no way should it bounce back. So it told him there's something very dense and very positive, okay, in the middle of this atom. And it's got to be a lot bigger than an alpha particle if it makes an alpha particle bounce off of it. And that's where he came up with the idea of the nucleus. A positively charged, very dense, massive piece inside the middle of the atom, okay? And that's Rutherford's biggest contribution. Now, sometimes people give him credit for discovering the proton. He didn't really discover the proton, but he discovered this idea that there was a massive positively charged, remember protons are positively charged center to the nucleus. All right, so that's kind of the setup. I just talked about all that and all that. So his conclusion: most of the atom's empty space with a small, dense, positively charged nucleus around which electrons move. So his idea then, again, this was 1909, so we're over 10 years later, right? 12 years, I think. 13 years? No, 12 years. All right, so what's happening is these electrons must be moving around the outside. That was his thought. The electrons aren't just embedded in this positive goo. Something positive in the middle, electrons are on the outside of it. That was Rutherford's thought. So his model is actually kind of similar to that classic model that you might see of an atom. So there's the nucleus, and it's a positively charged nucleus, right? And the electrons are kind of spinning around the outside of it. You remember seeing models like this? Oh, I'm such a good drawer, aren't I? So these electrons are spinning around, zooming around the atom, you know, in various places like that. So that's Rutherford's model of the atom. Dense nucleus, electrons spinning around the outside of it, okay? Notice that this is different than what we're going to be talking about later, which is Bohr's model, which shows the electrons in different orbits. This is more of the Rutherford model. And you guys might be familiar with that one. That's kind of like a Jimmy Neutron sign, right? You guys watch Jimmy Neutron or have watched it in the past? Not currently watching, I'm sure. All right, so one particle was still missing at this point. Basically, when we looked at that nucleus, it was way too massive to be explained with just protons, just these positively charged particles. And so there must have been something else in there. The protons are positive and they balance out perfectly with the electrons negatively charged. Now remember, those are balancing the charges. Their sizes were vastly different, okay? A proton is basically 1,800 times bigger than an electron. So take like a dime and then compare that to a milk jug, all right? So protons are huge compared to the tiny little electrons. But there was even more mass in the middle of the atom. And so what did we figure out? Well, a guy by the name of James Chadwick, and again, this is quite a bit later, right? 20 years later or so, he basically said, you know what? I think there's a neutral particle, doesn't have a charge, but it's just as massive. In fact, it's a little bit more massive than a proton. And that's what's making up both the alpha particles, 2 protons and 2 neutrons, as well as pretty much every other atom. It's going to have a lot of neutrons in it, okay? So neutral charge neutron, approximately the same mass as a proton, a little bit heavier. And when we talk about beta decay, it's actually kind of cool because a proton and an electron basically are the product of a neutron decaying. Okay, so neutron decays into a proton and an electron. So kind of cool. All right. So how do these atoms stick together? That's a great question. Now we've got these positively charged protons, right? And then we've got these negatively charged electrons. Opposites attract, so it makes sense the electrons would want to come into the protons. And the closer the charges are, the greater the attraction is going to be, right? The greater the electrostatic attraction or the force of attraction is going to be there. So it's holding these electrons close to the nucleus, okay? Now, if you are super bright, you might be thinking about the fact that, well, those protons are right next to each other in the middle of the nucleus. Why would like charges stay next to each other? Like charges repel. You are an amazing thinker if you're thinking that. And that is one of the universal forces that we don't understand, just like gravity. We don't really get it, but it's one of the universal forces. It's called the strong nuclear force, and that's what holds those protons next to each other. We don't understand that, but there it is. The strong nuclear force, it's one of the things that holds the protons together. There's also a weak nuclear force, and the weak nuclear force is what actually holds the quarks together in the middle of the proton. Yeah, we're not there yet, so don't worry about that. Holds the nucleus together. All right. So do we now know Thomson's cathode ray tube experiment? Yeah, we can do that. And if you were in class, I'd give you a chance to take a look at that cathode ray tube. When you come in, remind me. I'm going to have you look at that. It's pretty cool. All right. And then describe Rutherford's gold foil experiment. Yeah, you can do that. Now you can explain what happened with that gold foil and how his model was different than Thomson's, right? So your criteria for success: are you successful? Can you describe Thomson's plum pudding model? And can you describe Rutherford's gold foil model or experiment and model? A lot of times we'll call Rutherford's model the gold foil model. That's not really accurate. It's a gold foil experiment with then the nuclear model, the little Jimmy Neutron kind of thing. All right, well, so that's it. Real quick lecture today. I hope you enjoyed learning about Thomson and Rutherford, getting a chance to see how a couple scientists were able to dig into the black box of what an atom looks like by doing these other experiments. They didn't have a microscope and see this stuff happening. They saw the results. Thomson saw the results of the beam moving. Rutherford saw the results of the alpha particles, landing on that X-ray paper. And so they were looking at results and making conclusions about what happens inside and making a model, right? Scientists use models to describe things. And that model changed from Thomson to Rutherford's time. The model changed, and then it changed after that, and it keeps changing. We'll get to how it's actually kind of looking today. It's way crazier, way more complicated than what they had, but these are good models. They still help us to understand the atom, and they help us understand the process of the scientific method and how you can go about discovering things that you cannot see. Isn't science awesome? All right, have a great day. God bless.